Welcome back. We've now laid out some of the theoretical groundwork, and maybe you're getting tired of proving things about norms and inner products, and it's time to start putting this to practice. So we're going to talk about some transforms that are commonly used in signal processing. The first of these, and perhaps the most common, is the cosine transform. So the cosine transform is an alternative to the Fourier transform. And it has some very nice properties. For one, it is an orthobasis, and actually, technically, we're going to talk about this as being an alternative to the Fourier series, and we'll clarify why that is in a bit. So it is an orthobasis on 0, 1, or it could be, or we can choose another interval. In fact, if we have something on that's a basis on 0, 1, then you could always scale the signal and shift it. Scale it in time and shift it in time to make it an orthobasis on any other finite interval. So when we prove something's basis on 0, 1, you should view that as a wonderful, generic, useful thing, and not something that's limited to just 0, 1. So the cosine transform bases and the corresponding coefficients that they're real valued. And this is one of the things that makes it very useful. As you recall, the Fourier series is complex valued. And second, the basis functions have different symmetries. So this really comes into play when we're talking about things such as the discrete cosine transform and its relation to the discrete Fourier transform. And we'll get to that in a later lecture. But it's significant. Now, it should be noted there are actually multiple different cosine transforms that we can define. They're all called cosine transforms, but typically there's a Roman number behind them. Oops. And like I say, we will start with the continuous time, but then we'll get to the discrete one, because that's one we typically use in signal processing systems. So, for example, we have cosine 1, cosine 4 transform, and we'll talk about those. So the cosine 1, or the discrete cosine 1, is the one used in MPEG and JPEG. Compression. Okay, so let's get into it then. The cosine 1 transform basis functions for t in the interval 0 to 1 are defined as psi k of t is equal to 1 for k equals 0, square root of 2 cosine pi kt for k greater than 0. Okay, so I've put in here plots of the first 4 basis functions. So first we have psi 0, psi 1 of t, psi 2 of t, and psi 3 of t along here. So cosine functions, just like you would expect. The main difference that we're seeing here between this and, say, a Fourier basis is that the Fourier basis would have the DC term, and then it has integer periods of your waveform. So psi 0 and psi 2 would be in a Fourier basis, but psi 1 and psi 3 would not, because the first one's half a period and the next one is 1.5 periods. Alright, so let's run through an example and see how this works. So we'll let x of t be a signal on the interval 0, 1 that we've been talking about. And we're going to use the standard inner product and the induced norm. So we're going to now define a reflected extension of x of t on -1, 1. Okay, so this is going to be x tilde of t is equal to x of minus t from -1 t to 0, and x 0 just itself as before. So I happen to have an x of t that will just fit the bill, all ready to go. Here we are. Alright, we have an x of t defined from 0 to 1, and so let's see, right there, and we find that x tilde now is just going to be, as it's described, a reflected version, reflected right about t equals 0. Okay, so now we're going to take a brief detour to kind of motivate what we're doing with this example, and that is cosine. We're going to start with the Fourier transform of our reflected version. So going to synthesize x tilde of t in a way that we are used to. X of t is equal to the sum from minus infinity to infinity. It's k, e, j. Now we would do 2 pi k t over t. But t is equal to 2 now, from minus 1 to 1. So this becomes pi kt. All right, so x is real, or x tilde also is real. We'll have that alpha minus k is equal to alpha k conjugate. So we can rewrite this as x tilde t. Let's put the DC term out front. 0 plus, using Euler's identities, we get, I'm going to change this to a because they're not the same anymore. They're actually related by a factor of 2 or 2j depending on what we're looking at. 2 pi kt plus, since the complex exponential is made of sines plus I, or cosines plus I sine, we can just pull out the sines and the cosines separately. So here we have a0 is equal to alpha 0, and ak is equal to 2 times the real part of alpha k, and vk is equal to minus 2 times the imaginary part of alpha k. Well, great. What next? Well, next, we note that xt is even, so we won't use any odd functions to build that up. That should make intuitive sense. It's actually one of the homework assignments that I sometimes assign. I didn't do so this time, but if you're watching this in a later semester, maybe you'll be the lucky ones to have it. We can prove that if you have an even function, that the best projection into a subspace includes no odd basis functions. It's really not that bad, but we're not going to do it. So all bk's are 0. That means that x tilde t a0 plus k equals 1 to infinity cosine pi kt. There we go. All right. Well, where does that put us? So this works for any symmetric x of t, in this case x tilde, on the interval -1, 1. However, since x of t is just part of x tilde, we can now say kind of going the other way around, x of t is equal to x tilde of t for t in the interval 0 to 1. That's by definition. That's how we started out. So that means we can build up any function on the interval 0 to 1 using just cosines. Actually, x of t has got to have some constraints, but any continuous x of t, continuous and finite, continuous, finite on 0, 1 using only cosines. So now we have our cosine transform. The last thing we need to convince ourselves of is that we indeed have a ortho basis. We've now, I think, convinced ourselves that we have a basis. Is it an ortho basis? And we can see that vk, vl, or psi, I'm sorry, 0 to 1, cosine, the 2 out front came because of the 1 over the square root of 2, I'm sorry, because of the square root of 2 normalization in our definition. ILT, dt. Well, when k does not equal to L, then we're integrating periodic function over a full period, and this function varies between positive and negative equally. It disappears, and we can go through and do the full analysis, but it's just an exercise in algebra, and so we're going to skip that. And when k is equal to L, then we have a cosine squared function, and that can be written using a trig identity as 1/2 plus 1/2 cosine of twice the frequency. Well, integrating over the cosine part is 0. Integrating over 1/2 gives you 1/2. The 2 out front gives you a 1. And we're done. So back to, let's just close the loop on how this is related to the Fourier series. Because we just got rid of the sine part of our Fourier series, and we're saying, well, that works too. Well, what's the difference? So in essence, the cosine transform samples the frequency domain at twice this isn't said well, so I'm going to put it down, then I'll explain it differently. So in other words, what's going on is with the Fourier series, we're building up the signal with harmonics. And these harmonics range from the fundamental period and then multiples of that. But with the cosine transform on the same signal, we are also sampling harmonics, but not harmonics of the fundamental period. We're sampling harmonics of half that frequency. In other words, we get twice as many frequency samples as we do with our Fourier series, and that can be seen here. The starred in red basis functions would be associated with the Fourier series, but we have these other ones in between. So we're sampling at more frequencies than the Fourier series. And it turns out that that works to give us a really nice basis function. So I guess I could put it this way. Are spaced pi apart rather than 2 pi apart. So that's it for the cosine transform. We'll do the discrete cosine transform next.